Today we are going to view Chapter 9, Subnetting IP Networks. Designing, implementing, and managing an effective IP addressing plan ensures that networks can operate effectively and efficiently. This is especially true as the number of host connections to a network increases. Understanding the hierarchical structure of the IP address and how to modify the hierarchy in order to more efficiently meet routing requirements is an important part of the planning an IP scheme. In the original IPv4 address, there are two levels of hierarchy, a network and a host. These two levels of addressing allow for basic network groupings that facilitate and in-routed packets to a destination network. A routed forwards packets based on the network portion of an IP address. Once the network is located, the host portion of the address allows for identification of this destination device. However, as networks grow, with many organizations adding hundreds and even thousands of hosts to their networks, the two-level hierarchy is insufficient. Subdividing a network adds a level to the network hierarchy, creating, in essence, three levels: a network, a subnetwork, and a host. Introducing an additional level to the hierarchy creates additional subgroups within the IP network that facilitates faster packet delivery and added filtering. In early network implementations, it was common for organizations to have all computers and other network devices connected to a single IP network. All devices in the organization were assigned an IP address with a matching network ID. This type of configuration is known as a flat network design. In a small network with a limited number of devices, a flat network design is not problematic. However, as the network grows, this type of configuration can create major issues. Consider how on an Ethernet LAN, devices use broadcast to locate needed services and devices. Recall that a broadcast is sent to all hosts on an IP network. The Dynamic Host Configuration Protocol is an example of a network service that depends on broadcasts. Devices send broadcasts across the network to locate the DHCP server. On a large network, this could create a significant amount of traffic, slowing the network operations. Additionally, because of a broadcast is addresses to all devices must accept and process the traffic, resulting in increased device processing requirements. If a device must process a significant amount of broadcast, it will even slow the device operations. For reasons such as this, larger networks must be segmented into smaller subnetworks, keeping them localized to smaller groups of devices and services. The process of segmenting a network by dividing it into multiple smaller network spaces is called subnetting. These subnetworks are called subnets. Network administrators can group devices and services into subnets that are determined by the geographical location, perhaps the third floor of a building. By organizational unit, perhaps the sales department; by device type, printer servers 1, or any other division that makes sense for the networks. Subnetting can reduce overall network traffic and improve network performance. A router is necessary for devices on different networks to communicate. Devices on a network use the router interface attached to their LAN as their default gateway. Traffic that is destined for a device on a remote network will be processed by the router and forwarded toward the destination. To determine if traffic is local or remote, the router uses the subnet mask. In a subnetted network space, this works exactly the same way. In a subnetted network space, this works exactly the same way. As shown in the image, subnetting creates multiple logical networks from a single address block or a network address. Each subnet is treated as shown in the figure. Planning network subnets requires examinations of both the needs of an organization's network usage and how the subnets will be structured. Doing a network requirement study is the starting point. This means looking at the entire network and determining the main sections of the network and how they will be segmented. The address plan includes deciding the needs for each subnet in terms of size, how many hosts per subnet, how host addresses will be assigned, which hosts will require static IP addresses, and which hosts can use DHCP for obtaining their addressing information. The size of a subnet includes planning the number of hosts that will require IPv host addresses in each subnet of the subdivided private network. For example, in a campus network design, you might consider how many hosts are needed in the administrative LAN, how many in the faculty LAN, and how many in the student LAN. In a home network, a consideration might be done by the number of hosts in the main. Every network address has a valid range of host addresses. All devices attached to the same network will have an IPv4 host address for that network and a common subnet mask or network prefix. The prefix and the subnet mask are different ways of representing the same thing, the network portion of an address. If IPv4 subnets are created by using one or more of the host bits as network bits, this is done by extending the masks to borrow some of the bits from the host portion of the address to create additional network bits. The more host bits borrowed, the more subnets that can be defined. For each bit borrowed, the number of subnets works available is doubled. For example, if one bit is borrowed, two subnets can be created. If two bits are borrowed, four subnets are created. And if three bits are borrowed, it means 8 subnets are created, and so on. However, each bit borrowed, fewer addresses are available per subnet. Bits can only be borrowed from the host portion of the address. The network portion of the addresses is allocated by the service provided and cannot be changed. As shown in the image, the 192.168.1.0 address in the image, one bit is borrowed from the most significant bit in the host portion. It's the red one in the image. Thus, extended the network portion to 25 bits. This creates two subnets identifying by using a 0 in the borrowed bit for the first network and a 1 in the borrowed bit for the second network. The subnet max for both networks uses a 1 in the borrowed bit position to indicate that this bit is now part of the network portion. Since we borrowed one bit from the host address, we can see that we are now left with only 7 bits. We can calculate the number of hosts we can manage by adding to the power of the number of n. N will be the number of bits left. In this case, it will be 2 to the power of 7, which gives us 128 bits for the rest of the hosts. But the first address will be for the network address. And as shown in the image, when we convert the binary octet to decimal, we see that the first subnet address is 192.168.1.0, and the second subnet address is 192.168.1.128. Because a bit has been borrowed, the subnet max for each subnet is 255, 255, 255, 128. In the previous example, the 192.168.1.0 network was subnetted to create two subnets, each one for a switch, as you can see in the image. In the image, notice that the router 1 has two LAN segments attached to its gigabit Ethernet interfaces. The subnets will be used for the segments attached to these interfaces. To assign an IP address for each of the interfaces, it is necessary to determine the range of valid IP addresses for each subnet. As shown in the image, the valid range of host addresses is represented in the blue part, where the network address is when all of the bits in the host portion of the address is 0. This means the first address will always be the network address. the first host address is when all of the bits in the host portion of the address are 0 except in exception for the last one. We can see that in the image. And the last host address will be when all of the bits in the host portion of the address are 1 except for the last one. And the broadcast address will be when all of the bits in the host portion of the address are 1. This means that the last address always will be the broadcast address, and the first address always will be the network address. In the second subnet, we follow the same guidelines for the IP addresses. So, the first address always will be the network address, the last address will be the broadcast address, and the remaining addresses between them will be the valid host addresses that we could use. Notice that each subnet uses the subnet mask of 255, 255, 255, 128 to indicate that the network portion of the address is 25 bits because we borrowed one from the host portion of the address. In addition, an easy way to calculate the number of subnets available is 2 to the power of the number of bits borrowed. This will be 2 to the power of 1, which will be 2. That means we only can create 2 subnets. And to calculate the number of hosts available, we only have to do the math 2 to the power of the bits remaining. In this case will be 7 bits remaining because we borrowed 1. So it will be 2 to the power of 7